All right, guys. So if I speak kind of weird, it's because I'm recording for students I can't make it. So we just went over a warm up with this sample problem. Okay, at which points of your function will you have a horizontal slope? And you guys had this function. So what did you guys end up doing? What did you guys do? What steps did we do to solve this problem? Yes, Aaron.
Right, so first you take the derivative, which is going to be 15x squared minus 15x to the fourth.
Okay, so the derivative of f with respect to x is 15. How did you get 15, by the way?
The power.
Power. Very nice. So you took the exponent here, and then you multiply it to the coefficient, right? 5 times 3x. And what about the exponent? What did you guys end up doing?
Minus 1, so it's squared.
So it's 2, or so it's 3 minus 1. That'd be 2 squared, as you said. And then 3 times 5. X, and then this would be 5 minus 1. That'd be 4, right? So you guys got this here. Very good. Again, what does this represent? Can anybody kind of go over briefly what this represents, this function? What did we just find out? I know it's the derivative, but what does that mean? Yeah, Aaron?
Sort of what the slope's going to be at any point x.
So instead of finding before the slope at one particular point, we're coming up with an equation, or if we just plug in the point, you can find the derivative at that point. So let's say I put in the at the function when you're looking at this. Let's say you're looking at the squiggly function, right? And I wanted to find the slope at this point, like at x equals 4, and I can't tell what it is. It's kind of hard to tell by eye. I would figure out this equation, then I could just plug in the x, and that'll tell me the slope at that point. Does that make sense? Okay. So just to reiterate, some people kind of forget why they're doing calculus. They're just doing it to go through the motions. I like to reiterate in class why we're doing these things as much as I can, so you understand conceptually what's going on instead of just doing, this is just math, okay? Do not treat this, I think you might have treated math better than I did when I was a kid. When I was a kid, I just treated it as something I had to memorize, go to the test and get an A, and go home. Okay, calculus is the one math where you probably should pay attention and really understand conceptually. Okay, there's a lot of applications with it. Okay, yes. Now, what to do now? Where do we go now? How about someone besides Aaron? Can someone please help me with the next step? I don't know what to do, Mr. Wee. Okay, help each other out. Benjamin.
Set it equal to 0.
Okay, and Allie, why would Benjamin set this equal to 0?
So you can factor
Okay,
what
so,
x equals. You can factor the 4.
got it. So, well, how did he know to set it equal to 0 though? Why in particular are we concerned where derivatives are? Yeah.
Because you're finding it when it's at the horizontal slope, and then it would be 0.
Thank you, Christina. Yeah, because it's asking, like, I'm asking at which points are the slopes horizontal. That means that the slopes are 0. And then Allie, I think you want to get to the next point too, is you wanted to factor out like a common factor between these two, right? The GCF, the greatest common factor. And what would that be?
Negative 15x squared.
Oh, you did negative 15x squared? Okay, all right, that's fine. So you can have it in a, okay, all right. And then so I see that you wanted to have it in this way, right? 1, what is it? It would be negative 1 plus x squared, yes? So that way you can write it as 0 is equal to negative 15x squared minus 1, correct? Is that way? You like the form of that? That's very good. And then at this point, what else can we do? Is this it? Is this all we have to do? Can this be factored out any further? Yes.
You can do 1 plus x and 1 minus.
Oh, very good. Okay, so it'd be negative 15x squared. In this case,
You
the
could
way...
also-
X plus 1 x minus 1.
That's right. Yes, Allie?
You could also just, you don't have to factor. Just at the end, when you square root it,
Oh, that's
just do
true.
positive negative 1.
I see what you're saying. So instead of factoring out like this, right? Like this factors out into these two, you could have done this. X squared, and you set that equal to 0, correct?
Yeah.
And then you just say x squared is then equal to 1 because you move 1 to this side. And then if you take the square root of that, then you get x is equal to plus or minus 1. Very good sharing of knowledge here. Okay, that's a nice little tip there. Nice little trick that we should keep in the back of our minds when we're taking the exams or just in the future. when you have to do this in some kind of context. Okay. All right. Now what? Now this is basic algebra at this point, right? So what x value can I plug into this portion of the equation that we have here to make this equal to 0?
Are we still doing raise of hands or can we just
Yeah, just share. Just share. 0. How about over here?
That'd be -1.
X would be equal to -1. And then how about over here?
Positive.
Okay, so we have 3 potential points on this graph that have a horizontal slope. So it could look something like this, right? There could be 3 potential points. Let's just say this is actual, not df of x, but f of x. There could be 3 potential. There are 3 points basically where the slope is horizontal. If I wanted to take it one step further, though, to be a little bit more accurate, would this be the final answer? Just the x points? If you really think about it, okay? Yes, Christina.
Technically, you'd have to like put the y into so like 0, 0, -1, 0.
So, guys, you only really solved for the x values of where these slopes occur, right? But don't forget, we're looking at actual coordinates. That'd be, I'm sorry, so this would be like -1 comma something. This would be 0 comma something. And then this over here would be 1 comma something, right? How would you figure out the y values for that? Plug it into what?
Point.
Point slope or
The original function.
just the original function. Because remember, we're looking at the original function f of x. We use the df of x to find out where the slopes are 0, but these are actual coordinates. And then we're going to plug these coordinates into the original function to get a y value for each coordinate. Does that make sense? I'm not going to go that far now. I'm not going to go that step, but just keep that in mind. You didn't fully answer the question, okay? But you did find pretty much the meat and potatoes of the problem, okay? You just need the x coordinates. That takes the most amount of work to get to, okay?
On the test, are you going to want us to find the entire point as well?
I think I'll make it very specific if I do or I don't, but I think for the exam, if I remember correctly to what I have on my key, I think I just want the x coordinates. But just keep in mind, the AP exam might not just stop there. They ask you for the whole coordinate, which is perfectly reasonable, okay? All right, guys, go ahead and take out a piece of paper, and let's write some notes for today. Your section is going to be called 3.4, the velocity and other rates of change. Okay, so that's what I want you guys to write down, and then I will give you the notes I want you guys to write down.
The little one was kind of the hardest thing to just find the original function.
For this one, for this section,
Yeah.
yeah, to go back from the like a rate change of rate or rate of change function, and then have to go back to like it's a it is pretty tough. That is pretty hard. All right, everybody have this written down? Okay. If you just need it, yeah. Now we're taking notes, but I just wanted to kind of give you like a
I
Huh?
thought notes were no longer mandatory.
Oh no, you don't have to. I'm just saying like it's just optional, but I'm just saying if you're taking notes from class, then this is beneficial for you. Okay, this is what I want you guys to write down. It's about a page of notes, but we're gonna talk about everything from what's called position, displacement, velocity to acceleration. Might be a little, yeah, Nathan.
Are you recording this right now, like the voiceover?
Yeah.
Okay.
It can,
Random students.
I think when you if the people are listening to this, you probably sound like so.
I'll go up and say hi later.
All right, it's fine. Yeah, just letting you know. Yeah, I'm not trying to make you feel bad. I'm sorry about that. Yeah. Okay, so if you think about it, now I don't know if you want to use S because S can be misconstrued as a different concept that I don't want you to think about. If you need to, you can use this. You could write in D instead. But you'll see why I didn't choose D. Okay, you can use like a capital D if you want. Okay, because simply put, what this means is, let's say T. What do you think T stands for at least? Time. The position I call S. That's why I don't like this. Maybe I should call it P. Oh, I think P would have been better, huh? Yeah, let's do that. Let's change my
Also do delta x.
delta or X, okay? But let's just say right now that P, the position, is a function of time. That means in order to find out where you are, right? Okay, over time, let's say that I walk in a weird pattern, right? This is just how I walk in life, okay? So this is not an easy way to get through life, but you can literally,
It works though.
yeah, you can actually map out mathematically how I walk, right? That's called a function. That's why we're doing all this stuff in math, okay? And giving you all these algebra skills. In life or in anything, we want to find a trend and try to give it a mathematical equation. I don't know if you guys ever watched this movie, but it's called Pi. Some guy theoretically found out.
Pie or like American
Life of
pie?
Pi?
Oh no, it's a different type of
Okay.
pi. No, it's pi.
Mathematical.
It's a mathematical pi.
Wait, then when did you watch Pie?
Huh?
When did you watch Pie?
What's that? Yeah, I don't know what you're saying.
Okay.
I'm sorry, Nathan.
I'm not okay right now.
I think you're making sense. I don't know what you're saying. But basically, in math, you're just trying to map out like a trend or a pattern with an equation. In Pi, the movie, theoretically, this guy found out an equation that you could predict. With a few variables, you could predict the outcome of what's going to happen in the stock market. In that movie, people are literally killing to find out these equations. That's the whole point of math, is you're trying to, like in this weird way that I'm walking, you can try to mathematically create an equation that at any time I can put in any minute and I can find out where I'm supposed to be. Okay? Am I in position 1 or am I in position 2? That's called a function. Okay? That's what a function is. You put in the time, once you figure out what that function or equation is, okay, and then it'll map out where you should be, position. Okay? So that's pretty much the basis of not just this, but just math in general, right? We're just trying to figure out ways to map out trends and patterns, okay, mathematically. That's the skill that you need in life. Displacement, without looking, or you can look at this, but can anybody tell me the difference between displacement and position? What is the difference between displacement and position? What do you think is the difference between?
Change. Position.
What do you mean? The change.
Like from A to B, like how far did it move?
Okay, as opposed to what? How would you describe position? As opposed
Right. So basically, yeah. Sorry if I could.
To, you can get it. Yeah.
So position would be mapping out exactly how far I went, like so.
Uh-huh.
Whereas displacement would literally map out the direction from here to from there.
Okay.
Or no, actually it's the other way around. Sorry, my bad.
Okay. So.
It's how far you literally went versus direction.
Okay. Yeah, that's true. That's right. So position is just where I am. Am I in position 1, or am I in position 2, or am I in position 3? Displacement is the amount traveled. Does that make sense?
I like what you said.
All right. So it's pretty nice. It's literally the change in position from one position to the other.
Displacement is change.
Yes, the change that occurred in that position. So from position 1 to 2, how far did you travel? Here's the thing. It's a function of time. Remember that. You're plugging in time to see the position at one point, and then you plug in another time to find the position at where he is now. He or she is now. They are now. You subtract it from each other, and then you find the total distance traveled. Right? So that's what we have here. So hold on, I gotta.
Distance traveled is the displacement.
Yes, that's right. Okay. So this is where things get really complicated because people mix up velocity and displacement and so forth. Just remember, look here. It's literally the difference in positions. What sign is that triangle?
Delta.
Delta. Now, what does that mean? the change, right? So if you want to look at it another way, it's the change from one time to the other time, okay? So it'd be, I'm sorry. This is like the function at one time, subtract it from the distance, or subtract it from the position of another time. That's it. However, I could find the rate at how fast I went. How would I do that now? Anybody have any suggestions for what to do? I found out how far I travel, right? What would I need to do now in addition to that, finding out that distance to where I could find out how long it took me or the rate at which I was traveling? Yes, Aaron.
Define the distance by time.
You just simply divide the distance you traveled by the time it took to travel there.
You can also take the derivative.
Well, okay. Well, no.
Wait, doesn't that say you don't divide by?
Oh, for displacement. So that note I made to the right, okay, you didn't have to write that.
Oh, I see.
I made a very, very strong note. We're not dividing by time yet, okay?
For displacement, but for
equals what?
Distance over time is just speed or velocity. I know there is a slight difference, to be perfectly honest, okay? But there is a slight difference between speed and velocity, okay?
Velocity is directional. Speed is just.
You could have a negative velocity where a speed is almost like the absolute value. Doesn't matter which direction you're going. Speed should just be positive, okay? That's how we're interpret it in this class, right? All right. So here's velocity. You literally take the displacement and you divide it by the travel time. So you take the change in the distance or the change in the positions over the change in the time. And what that will look like is the function at one time, subtract it from another time, over time 2 divided minus time 1. Okay?
So
Yes, Allie.
distance or displacement over time.
Yes. So you can look at the displacement as being the distance traveled. Okay? Does that? Yeah, I don't want to confuse you there. But they're interchangeable, distance and displacement. Okay? But that's average though, right? Now, here's the new calculus concept of derivatives. I could find, so I guess if I'm traveling, right? Like, is my velocity, right? So like, is my velocity constant there, right? This is the,
No.
yeah, all right. What am I doing here?
Okay.
And if you see Miss Julie running,
You should run too.
We
Oh, wow.
really
That's
ever
good.
run out the door and then come back. Remember that video? You do it?
I'd be like, "Did you guys see?" Yeah.
Can you
No.
do it?
No, I can do that. Yeah.
Not even
A little
for
bit.
snap.
Not even for a snap. Okay, so instantaneous velocity. So the average velocity, like it's just the average between that whole span that I just ran from, like I don't know where I ran to. I ran from like here to the door, right? The average time, like if I just had to calculate the velocity on average of the whole thing, how fast do you think I went?
Pretty slow.
Pretty slow. Yes. Okay. So give me a number.
Just gonna go
10.
1 meter per second.
10 miles an hour, you joking?
Okay, so that's the average, right? Between the whole thing, from like this slow velocity, including this fast velocity, right? Okay. That's the average. What would you say my velocity is right at the beginning?
0.
0. Right?
Like
Like 2.
two.
Right? How about the tail end of my progression?
A mile an hour.
You said the average was 10, right?
I did.
You said the average was 10. What would you say the final tail end was?
Gotta be like
20.
20.
Okay. So you guys see the difference? I can take, if I want to take the velocity, at the tail end or in that instant, I would take the derivative. Okay? We already know how to do that.
Well, the derivative at a point, technically.
Yes. Yeah.
Yeah.
Derivative is,
Taking the derivative of the average velocity would be the derivative function.
I
Yes,
understood it until now.
Yeah.
okay, so the average velocity,
Yeah,
guys,
bro, he's got it.
average velocity is between 2 points. Okay? Like from my running example is from here and then where I was by the end. Okay? The average
So
velocity.
you would take the average and then And you divide it by time to get the velocity.
Yes, that's what you guys noted. That's slope. That's basic slope, right? Just like rise over run. The difference in y over the difference in x, right? The new concept is now if I know my velocity is changing the whole time, okay, it's fluctuating, then it would be beneficial to find out the velocity maybe at just where I was in this position right here.
So it's for specific, like place and time.
Yes.
Okay.
Yes. So both velocity, just one's average and one's instantaneous. This is what we're going to be working with a lot, instantaneous. We're going to be working with patterns where it's not like a constant thing anymore, or that taking an average will suffice. We're now looking at trends and patterns where it can fluctuate wildly. Okay, slopes fluctuate wildly. Okay. Let's go up here. So just a clarification, I said this is like 3.5. This is 0.3 was instantaneous velocity, then we go to acceleration. In between there, I like to reiterate, speed is just velocity without direction. What would that look like mathematically? You can hint, you can look at the notes if you want. What is the difference between speed and velocity when we're talking about numbers, actual like values now? We could talk about it conceptually, right? But Nathan says something with direction, but what does that look like in math? Yeah, Christina.
If there's a direction, it has like a negative or a positive sign.
Yeah.
So for speed, you take the absolute value, so it has no sign.
So it'd be like 20 west or something, and then the other one would just be 20 miles an hour.
Exactly. So look, I'm going 20 miles an hour. That's my speed, right? Okay, I'm going fast, right? What about this way? Am I going any slower?
No.
No, same speed, different direction. This is positive 20, right?
Yeah.
What about this way if I go back? Negative.
Right.
See the difference? So I got my running shoes today, right? I'm just kidding. It's not that at all.
You should work at it right now.
Huh?
You join you.
Yeah, you can join me.
We
Yeah.
should take a lap, just like how fast are we going? Calculate that.
Oh, that'll be pretty fun.
That'd be fun.
Yeah?
I'm down.
No, not now. All right, I'll keep that in mind in the future. So I'm trying to make AP Calculus more interesting. I'll just make you guys run laps. All right. Good. I like that. Okay, and so let's see. Okay, and then this one is a little harder to define. I can't really find a way to. I haven't developed a fun way to kind of like exemplify this, but the velocity itself can change. Okay, at any given point. That's what we call an acceleration. So, I guess what you saw there, my velocities kept changing, right? So at any point, my velocities kept changing, but the change in that is what's called the acceleration. Sort of like when you're driving a car, okay? At any point, you're at 30 miles an hour. At any point, you could be 40 and then 50. That whole progression in the different speeds, that's called an acceleration.
It's distance over time over time.
Yes, it's distance over, it's a distance over time over. Yes, it's the distance over time. It's the velocity. Again, the change of velocity over time. So you literally take the velocity and you divide it by time. So again, remember, velocity is distance over time, but you're looking at the change of that over time. So it's literally d over t, distance over time, divided by time. So that's why we look at it as distance over time squared. Anybody take physics? I'm speaking as if you took physics before. Freshman year, yeah. It's been years, okay? So I apologize for this. I will find a better way to explain that, okay, one day, right? Or maybe when we talk in private, I can find a way to kind of better explain that. Okay, so just to reiterate, though, you take the velocity. So v of t, right? You take the yes, Sally.
Are we gonna need to know how to calculate all of these for this?
Yes.
Are there formulas going to be given on the test?
Well, no. Sorry, Nathan. I didn't mean that to be a mean response. I was just like, I don't know how to say this, but no. It's a technique. You're just taking derivatives of functions, okay? So it's not like I give you one and be like, remember this for the rest of your life, okay? It's like I give you a function, you take the derivative, and then you have to understand what that derivative means. Is it a acceleration or is it velocity, right? So let's say I gave you an equation for s, just to find out my position. If I took the velocity of that, or if I took the derivative of that, I would find I would end up finding the instantaneous. Or I'm sorry, if I took the derivative of position, what would that tell me? That would tell me, I think, instantaneous velocity. And if I took the derivative of that, I would get acceleration. Does that make sense?
Yes.
Yes.
I had a question. So,
Yes.
is there a way to find it backwards? So if I know acceleration to find velocity, or if I know velocity to find position.
It's called integration or integrals. But yes, you could ideally, if basically you're like working with a power rule and kind of going backwards to see how you got there. That's one example. Okay. The hard ones are the ones that have been worked out from the product rule, and then you got to go backwards. Okay. Don't worry about it, guys. That was a very specific question to a student that had a very specific question. Okay. Doesn't mean that you guys are like, wait, what? Do I have to, what's he saying? Okay. Don't worry. Okay. Here is an example. I will get this from the book, actually. So this is literally an example from the book. So I'm glad you guys came. So this is, I think, hopefully beneficial that you guys came for this. Okay. Sometimes it's best to kind of look at it in the way that you guys will see it on your own, too. Meaning, like, if you see it through Mr. Wee's nice hand-holding writing, then you'll be like, oh, this is how it's always going to be. And then when you see just flat, dark, dry writing, you'll be like, where's Mr. Wee? It's not the same anymore, okay? Or not even just me. You aren't with each other, you know? So we're going to look at it as if you're just looking at it on your own. Right? Okay. All right. Okay. So let's take a look at this. Okay. A rock thrown vertically upward. Okay. Thrown up. Right? Okay. Reaches a height of 24t minus 0.8 t squared meters in seconds. That looks really scary, okay? But what I'm trying to say is this. I throw this guy up in the air, okay? And if I pause it, let's just say like after 2 seconds, I can plug in 2 seconds like that for t, and I could find out exactly how high it went, right? It's like pausing it, okay? It's like putting in pause. You're literally finding the displacement, right? So that's why I don't like S. S looks like speed, but it's really displacement. Okay, so it's like this. It's stuck there at 2 seconds. If I wanted to see how far I wanted to, how high it went, I would plug in 3 seconds. And it would, it would show me where I am at 3 seconds. Okay. But let's go on to the next part of the question. Whoa, whoa, whoa! Hey there, sir. Madam, where is this? Okay, all right. Okay. All right. I want you guys to work on A.
Oh.
Okay, so I gave you some information. Now disseminate it. What does it all mean? Get up now with a partner, okay? And please find the rock's velocity and acceleration as a function of time. How would you do that? I don't know. So the question is, I have a laser. I should really use my laser.
So just find the derivative. It's going to be 24 minus 1.6. That's going to be.
Yo, Aaron.
So here's the question.
Yeah.
Is that t squared like the last one?
Yes, it is t squared.
Derivative, which is going to be.
So 24t minus 0.8.
Please erase whatever you want. I have more whiteboards here. I got Ben, where do you sit?
No, it's lost.
Alright, I just didn't want to invade your space, but you're now living in.
The acceleration is just 9.8 meters per second per second.
On the moon.
Isn't acceleration just 9.8 meters per second per second?
No, but it's on the moon.
Oh, the moon. I'm sorry. Well, that's 6-ish.
Wait, you're talking about gravity or what you said?
Wait, what is it for the kilometers per hour?
I'm sorry, what did you say?
It's the reference of kilometers per hour.
Wait, oh, right
Why would
here?
it be
No, like, okay.
Oh, don't, no, it's not important. You're not gonna have to do.
So why did it tell us about kilometers per hour? So why did it tell us about kilometers per hour if we're not going to use it?
I don't. No, actually, I think it does come into play a little bit later, but I don't remember. I wrote notes and I don't say anything about kilometers per hour.
I think maybe they asked us to convert it at some point.
Do they? That'd be horrible. No, they're just being real big meanies. I don't understand. There's literally no reason why we needed that. Yeah. I think it's just I don't know. Yeah. It's just them flaunting their knowledge. Like, I know how to convert. So, simple as that. Okay, would anybody like to see the answers or no? No?
We need to find, well, yeah, sure.
Yeah, sure. Okay.
Yeah, it's around 6-ish. Oh, but they wouldn't function.
Yeah.
That's what because they're using the power.
All right.
So the second
Oh, wait, we need
yeah, it has a consequence.
I got rid of one.
Uh,
I don't think I did it right this
this week.
Yeah. Yes.
How much are you doing? And just the Friday?
Yes. This is a part A. Just part A. So, one thing. Hold on. Let me add one more thing to your answers. Okay. Let's add the element of units.
So meters per second and meters per second squared.
Okay, yes. So the first time whenever you guys plugged in a time, you got a distance, or you got some kind of you got some kind of a you got some kind of a distance, right? Or like position, okay? That's literally in meters. But if we take the derivative with time, that means it's changing over time. Over time, it's meters over seconds. And we want to find the change in the speed, which is meters over seconds. It's meters over seconds divided by seconds, which gives you meters per second squared. Okay. What does this tell you about the acceleration, by the way? Negative 1.6. What does that tell us about the?
Constant. No, it's constant.
Well, well, yeah, Like if you, it's. Would you say it was
Oh, yeah,
decelerating?
sorry, it is decelerating.
Why is it decelerating if I throw it up?
Because it's going after.
Yeah, even though I set it off at a speed, it's always like accelerating down. It's a force down. Okay, that kind of makes sense. That's what we interpret as like some kind of gravity. Okay, how come? By the way, does anybody know the gravity on Earth?
9.8 meters per second per second.
Ooh, Danny took it one step further. It's negative 9.8. She's good. No, that was correct. You gave me the absolute value. Very good. Danny was correct. Yeah, it is negative 9.8. Why is it different though here in this equation or
Because
this?
it's on a different planet.
It's on a different planet. That's right.
Or it could be the moon.
Oh, it's not the moon then?
Or that would
Oh, it's not. I don't know if it's on the moon. It's just on a moon.
The moon is like
Oh, it is.
It could be
It's on the moon. Okay.
Because the moon is like 6-ish stuff. I don't know. I think it's about 6.
All right.
Oh no, it's 1/6. So actually that makes sense. It's 1/6.
1/6.
Oh,
Oh, I didn't know that. No, I did not know that. I'm a science person too, and I didn't know that.
9.8 meters per second per second.
All right, let's do B. Stay up there. Stay up with your partners. Do B. How long did it take? Yes.
I still don't understand what you did.
Reach the highest point.
Oh, hold on. Let me go on over to you. Okay. Go ahead and work on this one, but let me go over. What'd you say?
So that, yeah.
You got it though. Me?
So now that we.
Oh, I didn't understand.
Do you remember?
Okay. So
How long did it take
this
to
is
launch
the equation for
Just gonna plug my eyes.
any point t. So
And the
here,
highest
the answer right there.
Here. Or the velocity would be zero.
Here, however, this is
It's like it stops. Yeah.
Oh, so I did this.
so you found
15 seconds.
Just right here, just like.
So the derivative
So-
nice
Oh, you want
I
to?
mean, that should have been 24.
Okay.
I just realized that.
Yeah, it's okay. Yeah, I was like, one. Okay.
This is what I meant.
It's good. That's perfect. So what's it?
Oh, that would be
July
24
to May.
would be the height,
And I took out the
but
negative
then we need to find.
just to make it expensive.
Oh,
So I think he's.
don't know.
Like, if I
Like,
set
I'll
it
grab my
equal to zero,
thumbs.
I took out negative
Yeah.
one,
Yeah.
and just, so that would just be negative 24.
Yeah, because I'm thinking about that. I'm like, mathematics.
No, we don't have to.
I just find it easier.
We don't need that. It's just 24.
Okay.
No,
We're not thinking that.
the high cancel.
Oh,
right.
Sorry.
Okay.
Okay.
Well, let's just say we got. Let's stay with the original.
Maybe
Make it.
Yeah, okay.
So now this equation, do you know what that represents? Like, what this is? This means that if I plugged in t, right? Like, so let's say at time 2 seconds, where this is the position at 2 seconds, right? 2 seconds. I can also, so I figured out position, which is at like the position, right? Position probably like what, like 4 feet or something.
Oh.
4 meters, right? I can also find out at that time now if I plugged in.
Oh,
Now this,
Like,
this, I can find out.
Personalized, yeah. Like how you have this thing.
Speed, I'll just say, I plugged it into the equation. That would be like,
Like how it's
20.
This is acceleration.
That's what you just was. This equation represents finding the.
We're science
So-
So
If I take the derivative of that,
point, it's right there.
we,
If that point was
negative 6. Oops.
basically, to remember is that.
It literally just tells
that's
me,
how you got that.
sorry,
Okay.
literally it just tells me any time acceleration did not change. So it doesn't
yeah,
matter.
I want to be this.
Yes.
Oh, this is the-
Oh,
I like her.
I mean, I feel better now because I was feeling like.
Yeah, so this is the change in distance over time.
Yeah.
So this is the change in the distance over time. Like, I know this is good for you to do S divided by t.
No.
Time.
Distance over, what would you say that? Distance over time, right?
Okay.
This was distance, okay? This was distance. This is distance over time. And then this was the speed or the velocity, the distance over time. That's the velocity, right? How did that change?
It was over equation. So the second
Like
equation
this.
is 24
You're driving a car?
So you take what you guys is here and put it on time.
Zero.
Yeah, yeah.
The highest point velocity is 0.
No.
Then we just
They did
solve
something
it.
for that.
So
No.
you minus
You-
24
You're on a
divided
something,
by
Danny. Just
No.
gotta fly.
It's not.
Liberate your thoughts.
No.
Why is
I
it
don't
making
think my thoughts are over out of your mind.
Think about it like this. You're in a
Physics and I forgot everything.
no. Let's think of it maybe like driving.
To the students that aren't here today, why are you in class? Where have you gone? We need you in our class. Okay, good talk. I'll be leaving you now. I'm gonna go do my work again. Bye.
Right? So what do you?
Never 30 on the freeway.
Follow me on Instagram at
What do you guys usually? You go to 6. Is it always 65?
No.
Be honest here. Some of you guys are demons. Don't do that.
I don't. I do.
Christina, no.
What other people see.
The point is, do you see that
Yeah.
these are speeds, right? These are miles per hour. It's not meters per time. It's miles per hour, right?
Yeah.
Your speed does change. So you can literally take that when the speed was like a minute ago as opposed to where it is now, and I can take the difference and I can divide it over time.
So acceleration is velocity over time.
Yes. So there's literally change, looking at the change in the speed and where it was in the minute as opposed
I
to.
don't understand how you do this.
Yeah.
Yes.
Because
Derivative.
it's still the change of distance over the change of time.
Just that one instance. Instance. The derivative is the concept of the
There's a better
derivative.
way you could have done that.
The concept, not the
No,
actual
second
derivative
eraser.
itself, is pretty much the same as slope, the change. Like or average change. Like derivative is slope, right? Like if you took a point here and here, you found the slope, right? The derivative is almost the same thing, but it's like saying the slope, but only at one point, just that one point. It's the same concept. So that's why if you think about it, looking at the change of distance over time.
So that when we find derivatives, like separately.
What's that?
Like when we find derivatives, these ones separately, or just
Well, it's just two different techniques. It's just one, you can literally just take the change of like you literally take 2 points and subtract them from each other.
It just like it's very clear. I like hit it on something.
That just gives you the average change. So that's for these two.
No.
This is the
I
average
don't
change
want that
for
on my.
If I wanted to find the change at one point, I no longer can use this technique. Do what's
Well, in a way we do, it's just the limit as used to us.
very good. Let's just, if we have to make sense of it in our head, just think of it as two kind of distinct techniques. This is where we take the derivative, like the actual mathematical derivative, and then this is just where we just take the change of two points.
And there's a velocity and acceleration. You do it once for velocity and then you do it the second time for the acceleration because it's like this is over time and then this is over time again.
Yes, exactly. So you took those. Yes. That's why exactly what that Huh? That was me for like 5 years, so don't do that. You can, but you're not gonna really keep it up.
That's very nice.
Alright, go ahead and have a seat, guys. Oh no, don't! We're not done. We're not done. Wait, did anybody solve for this? Besides Ben, I can see. Okay. Did anybody solve for this? B. How long did it take the rock to reach its highest point?
15 seconds.
How did you figure out that was 15 seconds?
Wait.
Alright. Wait. What, Allie? Wait. Yes.
Wait.
Yes.
So never mind.
No,
I don't know
please.
what's going on. I don't know.
Oh, it's okay.
Is
Okay.
that how you got your answer?
We will keep.
They're on the second part though. We just finished the
Okay, so you finish understanding the first part. Let's let's comprehend what just happened. Okay.
Yeah.
We did that. We got a little sidetracked, and we forgot that there's a part 2.
Yeah.
That's all. It's not you, but it was me too. I was like, oh crud! I had a question up there this whole time. Okay. So let's focus now on this. So So let's look at the answer. It is 15 seconds. How long did it take the rock to reach its highest point? What did you end up doing, Deja? Can you explain what you did to get this?
Yes. So we visualized a rock, and then at its highest point,
Uh huh. Yeah.
at its highest point,
Uh-huh.
time would be like 0. So we put that in the function.
That would be so.
You mean
It's velocity.
Something is 0. You're right.
Its velocity would be 0. So
Yeah, because
we plugged that
there's no
into
speed
the
here.
function,
Uh-huh.
And then we got 24, and then we divided that by acceleration, and then we had seconds left over.
Oh,
or
very
percent.
very good. So let's interpret what Deja said in words into math. That was actually very well said. Yeah. Okay. So we're looking. So again, this is just for B. Okay, that's not 6, but that's a B. We knew that the velocity at the highest point. Okay, so if I had to illustrate it, for this person that's watching. Okay, its velocity stopped. There's no velocity, so we take the velocity function and we set it equal to 0. We figured that out. It's 24 minus 1.6 t, and then we used a little bit of our math technique to find out what t is equal to. That tells us the time where velocity is 0. That's 15 seconds, right? Not too bad. Now,
Where is this from? Yeah, like what section is this?
this is 3.4. So maybe it was good that I pushed this to Friday, so you guys can work on 3.4 a little bit.
You're right. It's gonna be a lot higher.
Yes, because now the question is C. Now answer the question. How high did the rock go?
You now know the time it took to get there, right? But how high is it? Now what do we do, guys? Okay, problem solve with each other here. What do we do now? What equation do you use? Acceleration, velocity, or displacement? What do we use? Position? Or I'm sorry, it's position technically.
Well, I'm just gonna assume since we're trying to find positions.
Yes, you're not wrong at all. But well, show me, young. Okay, never mind. Forget it. You already did it. All right, that's perfectly fine.
That would be the next question.
You predicted well ahead of this. All right, well, just act as if that you've like, whoa, what is this? I don't
When does the
know.
rock reach,
Oh, you're not gonna see it. No, can't ruin the surprise, guys. Nope.
how long was the rock aloft? We can do that. Yeah.
What? How did you know that?
Well, because it's just the time times two.
I don't even know what aloft means. Sorry, I'm like trying to
When
interpret.
it was off the ground or was flying.
I see. That's very
And it also says the answer.
Dang it. Yeah, it's frozen too, so I can't cover it. Just be fair enough. That's fine. Yeah. So,
When did the rock reach half of its
all right. Anybody figure out what to do?
Not yet.
Trying
We're
to.
close.
Okay.
What? Oh, right. It's just half. We did it. No? We did it.
We got 1 meters.
Yeah,
This
we'll
is
make it.
meters squared.
It's pretty high. But considering what's in the air for 4 seconds, I'm not surprised.
Oh yeah, and it's in the moon, right? So you throw it up, it's just it's not as much deceleration happening to it, so you can throw it a little bit higher. It's interesting, yeah. Really, gravity is what's pulling down your throw.
No, there's an equation for escape velocity. I don't know.
Escape velocity?
Yeah. So what velocity you need to escape gravity?
Whoa! All right.
On Earth, it's I think I can tell you, I don't remember.
I think it's 11 kilometers per second.
Yeah, I don't doubt you. So yeah, that's what it is. All right. It's 11. What is it? Kilometers per second. All right, that's a fact. Okay. I always get tripped up because my finger is in still motion. It's kind of creepy. So it is very, very creepy. Okay. All right. Before I unveil the answer, what did you guys get? Okay, so let's check the work here. The answer is 180. Okay, so before I reveal how you did it, I'm going to ask you, how did you guys do this? The original equation, because I didn't clarify this very well. I need to clarify this. What is the original equation telling you? What is it? So it does tell you the position, but just to reiterate, it does tell you the distance traveled too. So yeah, it gives you the position. Yeah, I think it's more accurate to say the position. Yeah, so it's just, in any case, you want to find out what position you're at 15 seconds. So we plug that in. And you got 180 meters. And we knew that it took 15 seconds to get to that height, right? At that height, you're at 180 meters. Okay. So very, very good. Okay, so yeah, I think it is just position. It's not distance travel, but I guess it's just position. Yeah, it's just where you are in that time. Okay. Let me ask you a critical thinking question. If I put in, I like that. Yeah, as soon as I say critical thinking, you're like, all right, let's do this. Okay. At 16 seconds, what would the position be? Higher or lower than 180 meters? Lower. Why would you say that?
1 second later.
Starts coming back down.
Starts coming back down. Okay, so that's one way to really make the difference here in in this equation. It doesn't tell you the distance traveled. So I'm making that mistake right now in my head. Okay, it tells you just where you are in that instant. So you could be at position 180, and then 1 second later, you suddenly have a lower value. It just means you're at position 160 meters. Okay, does that kind of make sense? Okay. All right. Let's see. So that's its maximum height. When in the reach? Do I want to do this? I think I should. This is kind of hard. I don't know if you guys will.
Oh, you did it now or go?
Yes. Oh, Nathan. I like that. That's very good. Yep. So yeah, I can't be scared to give you guys this question. Let's go on to D. We have 2 more parts. D and E. There is a legitimate D and E, but yeah, Aaron.
Yeah, D is on the way up or on the way down?
D. When did the rock reach half its maximum? I think it's no.
Yeah, I think it's both. Yeah.
No, you're right.
It's when? It's time. So like.
No. Because it's on its way up or it's on its way down.
But we already found the maximum height, so like let's move on the way down.
It's just that I think the equation accounts for it if you look at it, because look at what is it? Is it no? It's position. Look at position. Okay, so that's the clue. Look at your position equation. Does anybody have the general position equation? Where is it? Does anybody still have it? Where do you still have it? Oh yeah, you do. Okay.
Also right there.
Follow my laser. Don't look right at it, okay? But it's on this whiteboard right here. You guys see that? With that squared sign, what kind of equation is this? Parabola or a quadratic? That infers that you might have up to how many solutions?
2.
Okay, so that might tell us that there's 2 different times that we are halfway up. Do you see what I'm saying? It could be on the way up or on the way down. As Aaron was saying, or we might be looking at it on the way down, or we might be looking at it on the way up. This equation accounts for that. You could be looking at 2 times. Okay.
Oh, so you want us to find both? Okay.
Yeah. So just yeah.
So both.
That's all I'm going to leave you at. That's all I'm going to say. Okay. So what do you do now with this equation and what they're asking for? When did the rock reach half its height? What are you supposed to do? Okay. Okay. Go ahead and solve. This is the problem that I'm giving you guys right now. I don't know.
What's the maximum height?
I don't know.
180, so
I don't know, guys. What do I do? I don't know.
90.
That's the first equation.
All right. I'll let you guys just work out your desk right here. But ask around though. Okay. Talk. Okay. If you're not in a conversation, just lean your head towards the conversation. Act like you are, so you can just listen. Right.
It has different speeds.
I'm just doing the 10 already.
But yeah, okay. I just I don't wanna. Solving parabolas is like the most painful or just annoying thing in calculus, because you have to go through all these other things and then.
You said that you go to the original.
Yeah. Plus minus b squared minus 4ac. Huh? Oh yeah, so I think we have the original function.
Yeah.
Plugging in 90 because that's half of the maximum height.
9?
That's half of the maximum height,
Oh, okay. Yeah, that makes sense.
and then it's all.
So then why? Because this, we make sure that we understand.
But the original equation has t.
That one, yes. Well, yeah, but we're solving in terms of.
Oh, are we making it equal to 90?
Yeah.
Okay.
What's 99? Positive 20.
Where did that T go?
Yeah.
What is this? It's 66.
Okay, just do the.
Oh, is that derivative?
Yeah, the first equation is for displacement. Sorry, solve. Yeah.
I'm just gonna wait to show you. Let me tell smoking about the pudding.
No, that was.
Context matters.
Anybody get any answers so far?
No, I need help.
All right, I'll come over and I'll help you.
I have no idea what I'm doing.
Okay, all right. Let's let me go over and
I
help.
guess it's a good time to refresh that.
I don't know what I'm doing.
Do you need to use your generator? Just
No, you just saw.
with the quadratic formula?
I'm not supposed to.
Any method is fine.
Yeah, because
I
you
would
back
recommend quadratic since
without saying.
0.8.
You can use that for the 90 workers. Now you can start using a formula. You can start. So I know it doesn't look like, like setting equal to 0 is like, what is it, aligns with the question that we're answering, right? But it's simply a way to figure this out, how to break the answer.
The mayor, the hair, and that too was.
So it doesn't look like it's answering the question, but
Oh,
it is.
yes.
So, setting equal to 0.
It's a e squared minus 4ac. E squared minus 4ac. Squared.
All right, it's b squared plus or minus.
No.
No. It's negative b.
Yeah.
Plus or
I teach this.
Negative
Negative
b plus
b
or minus
plus or minus.
square root b
Wait,
Negative
b.
She got
squared.
everything
Plus or
right.
minus
There's not.
square root b squared minus 4ac is all over 2 and
Well, look at my student that I did teach you. I can't take any credit.
they made us memorize it in 8th grade and they wouldn't let us into the classroom unless we could say it.
Our teacher
They would make you sit outside.
But you're literally the person that everyone could ask. So yeah.
So I have to with the leading as like successfully.
Yeah. So technically, you're right. You're absolutely right. You had it. Yeah. It is negative. It is negative. So yeah. So it'd be negative 0.8. Because at that point, what is your age? Yes, that's the whole thing. So that's very good. Okay. So as you guys are working on this, let me help you out with where it should look like. I can see some of you guys are already finished. That's impressive. Okay. Okay. So I do apologize it's taking a long time, but again, this is something I really want to do with you guys. So, it just kind of locks into your brain what's going on. Oh, we got. Oh, jeez. Okay. So I guess if you'd like to listen, you can, or you can continue on with what you're doing. If you're stuck, this will help you. Okay. So we found out the maximum height from C was 180. Okay. Seconds, I believe, or meters. I'm sorry, meters. That's kind of where we threw the object up in the air, and then that's where it was at 180 meters. We found out also that is 15 seconds of our time. That's where the rock was. Okay. We want to know exactly how much time it took for the rock to get up to at least half that way. Okay. Half that maximum point. Either going up or going down. Okay. Halfway and then still going up, or when it's on its way down. Down, halfway, and then down. Okay. So we're going to say 90 meters. And we're going to set that equal to our position. We want to find out the time it took for it to get to 90 meters. So if we write this out as where the position is, we set that equal to our general position formula, which I believe is 24 minus 0.8 t squared, right? Oh, sorry. Is it? No. Did I write that wrong? No, it's 24t, right? Minus 0.8 t squared. Okay. That's how you set it up. Here's a mistake that I do see people making, which is very common. So that's why I want to bring this up. I'm not trying to pinpoint, hey, what's going on with you? Okay. So 90 is equal to, you guys are trying to do this. 90 is equal to, and then you factor out t, right? And it'd be 24 minus 0.8 t. Okay. That looks like you could solve that,
but we don't really know. Like some people are like, do we do like I don't know, like completing the square, quadratic equation? Well, remember, in order to make that quadratic equation work, okay, negative b plus or minus the square root of b squared minus 4ac over 2a. In order to make that work, you have to set this equal to 0. So I know you want to set it up like that because it looks like it answers the question, but this, you want to make this equal to, you want to make one side equal to 0 and have the rest as a polynomial in order to make this work, okay? So we're simply doing this to where we can solve for t, okay? I know it doesn't look like it's solving, but it is. It's algebraically a way to solve this problem, okay? So it's, if we rewrite it in the order, in the standard order that we see most polynomials written, it'd be negative 0.8t squared plus 24t, and then we move the 90 to this side of the equation. That requires us to subtract it. It'd be minus 90, okay? Then you just solve that. You try to figure out like two binomials, okay, t plus something or t minus something, but we know it's not that easy. This one's kind of complicated. So this method, you can't like reverse FOIL or you can't complete this. It's not that easy. So that's why we use the guaranteed way to find out the roots. You plug in your A, which is negative 0.8, your B, and your C into this equation. Did anybody get the values for this problem? Yes, Christina.
I got 4.39 seconds and 25.6.
4.39, you said? Seconds. And what else did you get?
25.6.
25.6 seconds. Okay, so what does the 4.39 seconds mean? What does that mean?
So it's going up.
It's going on its way up halfway to 90, and then it gets to 180, okay? And what about the 25.6 seconds? Okay, so when it was going up, that was 4.39 seconds, but then on its way down like this, okay? This took us a total of 25.6 seconds. Okay, so if you want to look at the actual function now, this is the actual displacement function. Now if we're graphing it, look at it. Gets up to 180 right there, right? If we go to 90, that's about 4.39. You're absolutely right. Kind of like adverse from that, about 90 over here. On this side is 25.6 or so. Okay, so very good job. One last question before I let you guys go. How long was the rock aloft? Does anybody know what aloft means?
You didn't know that just a second ago.
I didn't know. Yes, Aaron's calling me out. I didn't know what that meant, so I'm like, what does aloft mean? And I'm the teacher. Okay, it means just how long was it up in the air. Last question. How do we do this? What? Stop it. Aaron, you're not supposed to just know it like that. Okay, well, maybe you do. Okay, what do we do? What do we do? Okay, so think about it. Okay, I'm going to give you like 2 minutes to think about it and then tell me what to do, and then we can go home after this. Okay, so what do we do? What do we do, Mr. Weeb? I don't know. What equation do we use? Acceleration, velocity? Do we use position again? I don't know. And how do we set it up this time? Huh?
But if you already know the maximum position is time, you don't really need to.
You sure? Oh, because you just multiply it to 2? Is that what you're saying?
Do we know how long
Very
it
smart.
took for it to go to the highest point? Yeah, it's 15 seconds, right? So then,
You guys are so smart.
wouldn't it be the
It's
same coming down? So just
In total, it would be. Yes. All right. We already have like 2 or 3 people that figured it out. Anybody figure this one out? No? All right. Let's answer this question before we leave. Okay. So last problem, guys, is E. Sorry, you guys aren't seeing this. Okay. So Nathan, guys, I'm sorry, guys. How long was the rock in the air? Now, Christina said Mr. Wee and Aaron, okay, not to discredit you, do we already know how long it got to its highest point? It was like 15 seconds. So we actually saw, so now I'm drawing as a curve, kind of like we're actually modeling after the function now. So that was 15 seconds, right? So it'll follow the same trend going down, right? So how long do you think it'll take in total? It took 15 seconds to get up. It took us 15 seconds to come down. That'd be 30 seconds. If you don't know how to set it up mathematically, you could also do this. Remember, we talk about position. What position is it at the end of the run? What position are we at?
0.
We're at 0. I know it seems scary, but you said 0 equal to s of t, which was 0 is equal to, I think, 24t minus 0.8t. And you must be saying, Mr. Wee, that's just basically telling us the beginning. That doesn't make any sense. Remember, you have a quadratic. How many solutions could you possibly have with a quadratic? 2 solutions. So one time, you're absolutely right. One of these solutions will be 0. Simply put, t is going to be equal to 0. Because at t is equal to 0, your position is equal to 0. However, if you solve this equation, okay, you'll get t is equal to 30. And if you don't know how to do that, this is how you would do it. 0 is equal to 24. I'm sorry. I'll factor out the t out of both things. So it would be 0 is equal to t times 24 minus 0.8t. This is where t is equal to 0, right? That's one solution. The other solution, well, you would just set this equal to 0. 24 minus 0.8t is equal to 0. And if you want to do the math, it'd be 24 is equal to 0.8t. You divide both sides by 0.8. And if you plug that into your calculator, you should get t is equal to 30. Okay? You can do it like the way Danny did it. She just did it in her head. She knew it took 15 seconds to get to the top. It'll probably take 15 seconds to get to the bottom. If that doesn't satisfy you, you can just set this equal to 0, and you get 2 solutions. Okay? Anybody have any questions about this one? If you have any more questions, please stay after class. I do have tutoring time, so we can talk a little bit more about this topic. Otherwise, you guys are free to leave. Good luck on the rest of your exams this week, and my exam will be on Friday. Okay, Nathan, I am expecting you on Thursday because you asked to take it on Thursday. Okay, all right. Thank you, guys.